So this is joint work with Ligia, Sa, and Rahul. Other Rahul, not Rahul Londo. Good. Good. So this talk will be about proving complexity lower bounds, and probably the one fact we know very well about lower bounds is that they are going to be hard to prove, or at least currently they're hard for us to prove. We don't know a great deal of them, but we know they're going to be hard. And in a high level, the reason why is we know many barriers, and I'm not going to go over them because I think you all know them. And as you know, the high-level summary of these barriers is that standard methods we use to reason about generic computation cannot resolve most open problems between complexity classes. So we apparently know a lot about what strong lower bounds cannot look like. Okay, we know many limitations on how such proofs must proceed. Okay. Oh, I realized I started late, so maybe someone just send me a message in the chat if there's some audio issue, like about like when I should be, like say 5 minutes before I'm supposed to stop. Yeah, would be nice. Great. So the starting point of our work, all right, thanks, is a simple question: what could a proof of PWMP look like, right? So we know a lot about what it cannot look like, and many weaker questions like NX different from BBP, X different from ZBP, so on. Can we identify properties that such lower bounds must possess? Okay, so instead of barriers, can we identify obligations that strong lower bounds are just going to have to obey? Okay, another way of asking this is saying like, what properties are we missing from lower bounds we know how to prove, like the things which fall under the barriers, but we'll have to include in a proof of NX different from BBB, for example. And so in this work, we provide a partial answer. I'm not going to say it's the answer in any sense, but I do think it's an interesting way of approaching the question, and it will discuss a way in which algorithms will have to be central to resolving major lower bound questions. Okay, so just to get a handle on this question, let's revisit what it means to prove a lower bound. Okay, so let F be some decision problem, and let A be some class of algorithms. Okay, so a lower bound that F is not an A is a claim of the following form: for all algorithms A in the class A, there are infinitely many n, and there exists an input x of A of length n, so that A gives a different answer from F. Okay, so for every A, someone has to respond with a bad input x of A that confounds the algorithm A. And in fact, we should construct infinitely many bad ones, because if there are only finitely many, they could be, say, hard-coded into another larger but still finite algorithm. Okay? So we're going to look at the complexity of the lower bound in the following sense. So we fix the lower bound problem A, okay, and we fix an algorithm A. We want to know what is the complexity of constructing a bad input of length n. Okay, so we're given a length n, let's say in unary. We want to know what's the complexity of constructing a bad input for that algorithm A. Okay, so the literature on lower bounds, broadly speaking, gives about two types of answers for this. Okay, the first kind of answer is that there are random or non-constructive ways of choosing the bad input x of A. And these are generally proofs relying on counting or information theoretic arguments, some kind of compression type argument. So it's just saying that there's sort of too many possible bad inputs, say, or if I pick a random input, so according to some distribution, I can prove with non-zero probability it fools A, and so on. Okay, so various proofs of time-space lower bounds for explicit problems in P work in this way, in type 1. Okay, so there's another type, type 2, and this is where you get some efficient way of choosing x of A, and these generally follow from diagonalization arguments. So the standard proof by diagonalization that the halting problem is undecidable, actually, it gives you an efficient way of producing a bad input. So given the code, the Turing machine that purports to solve the halting problem, you can effectively produce a bad input in which it fails to correctly decide halting. Okay, And this idea of focusing on bad inputs when thinking about lower bounds is quite old. For, I mean, even so, another example is the Myhill-Nerode theorem from the 1950s says that language is not regular if only if there's this infinite set of bad strings. Force every possible DFA to need infinitely many states. So there's even characterizations of lower bounds in this way. Okay. So we're interested in like well, which of these two types is the type we should be focusing on? So our starting inspiration is from a beautiful paper of Gutfreund, Schaltiel, and Tashma from 2005, who showed, roughly speaking, if P is in from NP, then bad inputs to stat algorithms can be efficiently constructed. So they can have type 2 lower bounds. So there's efficient ways of producing the bad input. Okay, so the following theorem can be derived from their paper. So for every fixed constant k, and for every n of the k time algorithm a, there is an algorithm R sub a refuter, going by the terminology of Valentine. It says that for infinitely many n, this refuter, given the string of n1s, outputs a formula of length n, which is satisfiable, but the algorithm reports unsatisfiable. Okay, and furthermore, this refuter runs in polynomial time, but it's a longer polynomial amount of time. Okay, so for every single algorithm, there is some algorithm running a bit slower, and it takes more time. In fact, it's running A inside of it, and it's going to produce bad inputs for that algorithm A. Okay. All right, so let's make this formal. Let's kind of abstract out what's going on. So say there's a P constructive separation that F is not an A. If for all algorithms in this class A, there's a polynomial time algorithm, R sub A, which for infinitely many n, given the string of n1s, will output this bad input. Okay, so we'll output some X sub A on which F and A give opposite answers. All right. So another way of interpreting this GST result is that if P is in from NP, then there's a P constructive separation. So if P is in from NP at all, then there is a lower bound of this type 2. There is a way to efficiently construct the bad inputs for any possible polynomial time algorithm. There is some refuter which will refute it. Okay. All right, so I'm just putting it back up there, reminding you what this is. So then our question becomes the following type of thing. So we want to know which lower bound problems require constructive separations and which do not. So here we're saying P versus NP basically requires a constructive separation. Like if the separation is true at all, then there is some constructive means for this. So there is some kind of type 2 algorithm which follows. And this is an algorithmic question about the nature of the lower bound. So what algorithms are implied by the separations? And so in our paper, so this appeared in Fox 2021, we argue that constructive separations are key. So we're not saying they're the key, we're saying they're a key to proving major separations between complexity classes. Okay, so the first broad series of results we prove says that essentially all open separation problems regarding polynomial time, including randomized polynomial time, are going to require constructive separations. Okay, so for all classes C, which could be P, ZPP, BPP, and all D, which could be MP, P space, X, and X, we have even more in the paper. If the separation holds between C and D, then there's a C constructive separation that C is different from D. Okay. Now I didn't define what ZPP or PPP constructive separation is, but it's a natural extension of what I defined before, just with randomized algorithms. So we generalized the GST05 paper, which was for P different NP, to hold for many different C and D. Okay, a couple of these other cases were known too, but almost all of the cases were not. Okay? And I just refer you to the paper for this. The main lesson here is that these kinds of separations against polynomial time are going to imply constructive separations. They're going to imply that such algorithms of these kind of type 2 lower bounds must exist. Okay. Now, what about the type 1 lower bounds, for which we know lots of examples? Right, there are these type 1 lower bounds, like are they could they be made type 2 lower bounds? Could we take something which, picking a random input will prove that it is bad, and turn it into some constructive problem where we can construct a bad input? So what we show is that making many known lower bounds constructive using the ones that are proved via counting arguments, that actually requires resolving other major lower bound problems. Okay, so just to give one example, just a simple example. I'm not even sure this is in the paper anymore. It's like a really simple example. So there's a theorem of Moss from the 80s that says that the language of palindromes cannot be solved with non-deterministic one-tape Turing machines in subquadratic time. Okay, it's a very classic type of lower bound. So one kind of theorem we can prove, among many, says that making this lower bound P constructive implies that E has functions of exponential circuit complexity. And making it P to the MP constructive, where I get to call an MP oracle so I can simulate the non-deterministic one-tape machine, this would imply E to the MP has functions of exponential circuit complexity. So constructivizing this lower bound implies universal derandomization, in fact. So, right, like you can prove it by some kind of counting argument, and making it constructive will just allow us to de-randomize all randomized algorithms. Okay. So our first set of results shows that if we manage to prove a good separation against polynomial time, then we're going to get a constructive one also, whether we like it or not. So we might as well think about constructive ones. In the second set of results, I'll give some more examples, I think on the next slide, is that this shows how much more powerful constructivity is compared to other methods. So if we can make these lower bounds constructive first, then we'd already be resolving major open problems. So the point is constructivity is a property we actually want of lower bounds. It's like the opposite of a barrier. If you can make it constructive, this seems like a very good thing. And it can only help you prove stronger lower bounds. All right. So let me say a couple more examples of these results. So another one is from randomized streaming algorithm lower bounds. So many problems, including simple ones like disjointness, are well known to require linear space randomized streaming algorithms. Okay, and this this just follows from communication complexity arguments. So one kind of theorem we can show is that for any problem in MP whatsoever, if P to the MP constructive separation, showing that this problem pi doesn't have super logarithmic space, let me find my laser pointer, super logarithmic space randomized streaming algorithms, this implies X to the MP is different from PPP. Okay, so right, we have things like disjointness, and we know they don't have linear space. Taking like say SAT, and proving SAT has a P to the MP constructive separation from super polylog space randomized streaming algorithms, that would imply a major, well, embarrassing, but still major open problem. It's embarrassing, it's still open, but yeah. So kind of making these like simple known lower bounds constructive would have major consequences. And finally, another category of our results is in randomized query lower bounds. So consider like the coin problem or the promised majority problem, where you want to distinguish bit strings that have a greater than half plus epsilon fraction of ones from strings with less than half minus epsilon fraction of ones. This is well known to require theta 1 over epsilon squared queries. Okay, and so we can show, for example, that, well, this coin problem can actually be solved in AC0, and that goes back to Aitai. In fact, uniform AC0. So we can show that if you had a uniform AC0 constructive separation of promised majority from randomized query algorithms, which use fewer queries than the lower bound, and say poly 1 over epsilon time, this implies P different from MP. Okay, and like if you had instead like an NC1 constructive separation, so you had some NC1 circuit, which given for like sort of for any randomized query algorithm that cannot compute promised majority would be able to print bad inputs for that algorithm, we would prove that P is different from P space. Okay. And there are more results in the paper, including results for many attendees' favorite problem, MCSP. Okay. All right. So, oops, there's a question. Are all of the bits of the hard inputs equally important? Well, that's an interesting question. I don't know. I mean, probably not, but to get to say why would take a while, I think. But maybe we could talk about it offline. Yeah, Pericles is asking, are all the bits of the hard inputs equally important?
It's hard to talk about offline.
Oh, sorry?
No, please go ahead.
Okay. So going back to this slide we were looking at earlier, we have two main messages which can be reinterpreted in terms of the slide. So recall, there's like two ways to generate bad inputs, right? Type 1 and type 2, right? So first, we show that in order to prove major complexity class separations, we need type 2 lower bounds, okay? Those that provide efficient ways of choosing bad inputs. And then second, if we can manage to turn various well-known type 1 lower bounds into type 2 lower bounds, then we'll get other circuit complexity lower bounds, okay? So type 2 seems to be like the real ideal of the kind of lower bound we want, okay? All right, so how much time do I have left? I want to think about like which slides are 10 minutes. Okay, all right. So let me say something about the GST05 result. I mean, it's not my result, but it's important for our results, and I feel like more people should know about it. So I'm just going to spend some time talking about it. Okay. So if P is from NP, then for implementing input links, bad inputs and algorithms can be efficiently constructed. Okay. So here's a simpler case. I'll look at this case, but it can be extended to decision as well. So the first case is to get a refuter for an end of the K time algorithm that's trying to print a full satisfying assignment, okay, when it exists, okay? So it first attempts to print one, and then it checks whether it actually satisfies, and it just reports unsat if the assignment attempted to print it fails to satisfy. Okay, let's just assume that our algorithm has this property, okay? So in that case, all of our bad inputs are satisfiable formulas on which A prints unsat, okay? So that must be the bad inputs, because we're checking like, whether the assignment we get is actually satisfying or not, okay? So the things that will make us make a mistake are satisfiable formulas in which we printed a wrong assignment or we just conclude unset. All right, so here's what the refuter would look like, okay? So on 1 to the n, we'll construct a formula f sub n that encodes the following property, okay? There exists a formula G of length n and a satisfying assignment to it, so that A satisfies G, makes it print 1, and if I run A on G, it outputs unset. Okay, so think of a formula f sub n encoding this purple property, which exists by the Cook-Levin theorem. I mean, this is an NP type statement because A is a polynomial time algorithm, so we can encode it with some kind of formula f sub n. Then we run A on f sub n. Okay, if A prints some G prime, right? If it prints some formula G prime, then we output this G prime. Otherwise, we output the formula f sub n. Okay, and so note that like, right, this thing, because it's simulating it into the K time algorithm in it as a formula, it will have into the order case size. Okay, so what are we doing here? So we are asking A to print its own counterexamples, basically, right? If it manages to do this for implementing n, if it manages to print its own counterexamples, like things like this, then we're done. Okay, but if it doesn't even do this for implementing n, then f sub n is printed for almost every n. Okay, but because P is in from NP, this f sub n formula must be true for implementing n, right? If P is in from NP, we know the algorithm can't work, so there must actually be some G on which A has this property. Okay, so when we're printing this f sub n, we'll still have implemented counterexamples being printed. So this refuter is going to work infinitely often, assuming P is in from NP. Okay, and there's a way to generalize this for deciders, which I'm just going to have to skip over for lack of time. Let's see. Maybe I'll talk about how to make what? Okay. Okay, I just heard some like robotic noise. Okay. So making one-tape Turing machine lower bound is constructive. So recall there was this lower bound of Moss that palindromes is not in non-deterministic one-tape subquadratic time. And the theorem was that I'm going to say here, making it p to the mp constructive implies that e to the mp has functions of exponential circuit complexity. Okay, so let me just sketch how this thing goes. It's really simple, and extensions on this trick is used many times in the paper. This is like the simplest version of the trick. Okay, so the idea is we're going to make a one-tape Turing machine, non-deterministic, that actually runs in subquadratic time. Okay, and correctly decides all palindromes of length, let's say, capital N, power of 2, with circuit complexity less than 2 to the epsilon little n. Okay, all right. So we're going to make a non-deterministic one-tape Turing machine which succeeds on all compressible palindromes. Okay, all right. So once we've got this is just unconditionally true. Okay, once we've got this, any p to the mp algorithm that can print a bad input for this one-tape Turing machine must be printing the truth table of a hard function, right? It must be printing some palindrome of length, some 2 to the n, and it has circuit complexity greater than 2 to the epsilon, because our non-deterministic machine runs in subquadratic time and handles all those with low circuit complexity. Okay, all right, and so then the consequence for e to the mp follows by a standard padding argument. So how can we get an m that has this property? Okay, so M guesses a circuit C of size capital N to the epsilon, encoding the input, right? So it tries to guess some compressed version of the input and guesses, let's say, the length of the input. So then, even on a one-tape machine, it can drag along the description of the C in capital N to order epsilon time as it reads the bits of X, okay? It's going to verify, as it's dragging along this N to the epsilon size description, that the truth table of C really is X. Okay, the input X. And then it verifies that X is a palindrome by using C to do random access into the X. So it'll use C to check that the bits of the second half of X match the first half in the appropriate way. And it's going to use the length of the input to determine when to start checking the second half, like when to switch over from first half to second half. But the point is that, like, once I guess this small circuit now and verify that it actually encodes the whole input, now I have random access into the input, and I can just solve palindromes and many other problems as well. Palindromes just happens to be, a standard one that's easy to think about. All right. This is just like one example of like the many kinds of results that we can prove from similar ideas, but there's other ideas going into promise majority and so on. Okay. So I want to end with some open questions, some that I think are pretty important for this work. So, for example, the relativization barrier tells us that direct diagonalization-based proofs are limited, right? We can't just directly diagonalize one class against another and get Peter Mimpi. But we do know that any major separation against P or BPP or ZBP is going to require a key property of diagonalization-based proofs, this ability to efficiently generate bad inputs. And so the big question is, what other methods of proof could yield this consequence besides direct diagonalization? I mean, maybe this is the question to think about next. Like, we know that diagonalization can do it, but we know that diagonalization is limited. But there has to be some other way to efficiently produce bad inputs in your lower bound argument. And so I think it's a very important question to try to understand. Another open question is, what about separations against smaller things like log space? In C, ACC0, does MP different from log space imply some kind of constructive separation? This is something we didn't really tackle. We were just thinking about polynomial time. It's much easier to reason about, but I think that you should be able to get similar results along these lines, but we haven't worked it out yet. Okay. Finally, remember that we had these things saying that if you can make certain non-constructive lower bound arguments constructive, then we could de-randomize. Okay, and some of these arguments really do boil down to picking a random input. And so what we're really asking is, can you construct this random input, which will carry out the argument? So you might ask, well, okay, are there equivalences between just universal de-randomization and constructive separations based on some version of probabilistic method where I'm picking a random input and proving that it fools the algorithm in a certain way. Maybe these two are actually equivalent. Maybe constructivizing no lower bounds is really derandomization in disguise. Okay, that's all I had to say. Thank you for your attention. Everybody stay safe.
Turn this off. Can you please turn off this off? Yeah. Are there any questions?
Yeah, right.
Hello, can you hear me?
Someone's going to have to repeat the question. I'm sorry. I just heard a blah, 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 something like that. Sorry.
The question. Go ahead.
Hello, can you hear me?
Lin, maybe you can type your question and your audio isn't.
It's okay, I'll repeat it for now because we have to move forward. Yeah.
Okay, can you ask Ryan if he has thought about almost everywhere refuters where you produce for all input lengths, and what does he think about this?
So Igor is asking, have you thought about almost everywhere refuters where what?
Where you produce hard instances for every n, and whether it's significantly different than this.
Where you can produce hard instances for every n that are significantly different.
Yeah, whether there's like major differences, or whether we can hope to also get this kind of refuters.
Okay, do you understand the question?
I only got audio halfway through the question
Okay.
at best. So
Yeah, maybe I can just. Can you hear me, Ryan?
yes, I can hear you.
Yeah, so
How's it going?
you mentioned some infinitely often results, so you get like you produce hard instances infinitely often. Have you also
Yes.
thought about like producing hard instances for every n, and whether you think this is going to be like significantly different or harder to do things?
Oh, so like if I prove that MP is like not an IO P or something, whether it's such a thing. It's a good question. I haven't thought through the arguments, but yeah, it's an interesting question. At least some of these arguments should work, but I'm not sure if all of them would, because it's like several kind of layers of indirection going on, and sometimes you actually are exploiting the fact it's only infinitely often. Yeah, so it's a very nice question though, because that could be useful if the hard input is doing something for you, and you want to use it in another algorithm. Then you would want it to exist almost everywhere or something. Yeah, very nice question. I'm not sure. I have to just sit down and work it out.
Okay, thank you.
So one more question is from Hanlin.
Okay.
Says that it's tagged in the title window, in fact.
Oh, I see it. Yeah, and some applications in average case complexity. Are there any applications of your paper in average case complexity? I don't know. Yeah, I mean, their applications come about because they work against randomized algorithms as well, and they're getting small inputs. Yeah, this is also interesting. Like maybe it's easier to construct, even easier to construct the bad inputs if you have a like average case lower bound, something stronger than a worst case lower bound. That would be interesting. I don't know. This is a plausible idea.
And one last question. Yes, exactly.
Yeah.
So Mike is kind of clear.
Okay.
Does your constructivization proof relativize? So if PA is different than NPA,
Yes.
is there an algorithm?
Yes. It, as far as I know, it does. Yeah. Yeah.
Okay. Thank you, Ryan. So we'll move with the next speaker, who is here, right? Okay, thanks a lot.